think back to the science and engineering, think back to the science classes that you visited, and and make connections to what you've observed and to these practices here on the right-hand side. So pick an ambitious science teaching practice and describe how you've seen teachers engage in this practice with their students, or how might a teacher, if you haven't seen this, how might a teacher engage in this practice with their students? So we're going to give you a minute to think about this, and you can type your responses into chat. And also we'd like to have you maybe voice some. What have you seen? What have you maybe seen in terms of teachers eliciting student ideas, in terms of teachers supporting ongoing changes in thinking? Jose, can you share with us one instance of you seeing one of these?
Sure. Good morning, everyone. So I was just typing in the chat right now. As I go into classrooms, something that's common that stands out is students routinely engage in explaining and evaluating and revising their thinking. So one that stands out is an 8th grade classroom, and students had to build these toy cars, and they were launching them down this ramp. And the goal was to see who could build the fastest car and explain why that car was the fastest. And obviously there's a connection there to weight and et cetera and aerodynamics. But as students were engaged in sort of creating these and shooting them down these ramps, which I got to see, they were then to just constantly, again, as they saw different cars coming down, be part of that revising process of explaining sort of what they were seeing and why that was happening.
Awesome. Thank you so much, Jose. I appreciate you. Soraya saw Forces Lab that pressed for evidence-based explanations. Thank you. That was at Lincoln High School. At Orchard 2C, Melanie talks about visiting 6th through 8th grade science classes and observing the ambitious science teaching practices, specifically with 8th grade science and the forces in motion. Thank you very much for sharing that.
All right. Good morning, everyone. Thank you for joining us. My name is In-Young Lee, and I support science instruction for Southgate and BCM communities of schools. And this is to remind us that our work is grounded in the 3 levers that are instructional drivers for the year. And at the center, of course, is student voice. That's been the highlight from this morning. With the levers, we wanted to show that our work in this session will be focusing on the first 2 levers to amplify student voice. The first being deep clarity of learning goals, meaning we need to be clear about what NGSS standards are, the 3 dimensions of them, so that we can make learning targets and objectives clear to our students as well. And the second, the bulk of our new learning today will be on the second lever, building precision of pedagogy. And that's where those ambitious science teaching practices that Craig mentioned will be coming in. So to remind ourselves that science instruction today should look different than the way that we experience science instruction as students. And those 2 shifts can be summarized like this. The first difference is that students should be driving the learning to make sense of relevant phenomena. That means that we can contextualize science learning so that instead of approaching it by topic, students try to make sense of something that motivates them to figure something out. The second would be making sure that students have a 3-dimensional learning experience. And that means that students are engaging in practice-centered tasks that are purposefully selected by the teacher, sequenced in a way where it allows students to construct meaning. So then how does that look in a unit or in lessons? This is what we can do to make sure that our science instruction is three-dimensional. So we know that we have topics or science content that we want students to learn, and that's our DCI or disciplinary core ideas. But that's not it. We don't want to just present what students should figure out. We want to give them ways to do that. And those are the SEPs or science and engineering practices. So we have 8 practices. These are the student moves that are across the board, K through 12. And these are how students are going to figure out the DCIs. Now, we can also challenge students to think about science through specific lenses, and those are our cross-cutting concepts. These are ways that scientists think, how students think about what they're figuring out. And the pluses at the top show that we can aim to have at least one of each of these 3 dimensions in every science learning experience we create for our students. And why would students want to engage in this? Well, that's the phenomenon, and that's the bottom here of the why. If we present science learning in the context of real life situations or things that students are curious about naturally, then we're giving them a why, we're giving them a purpose for figuring something out. And this is an image that we're familiar with from previous years. So our work with the 3 levers supports what we've been doing with our instructional core. And we know that the task at the center is informed by what students do, what the teachers do, and the content that we are responsible for. So in science, there's something unique about our standards because not only are the standards covered by content, but the student practices themselves are part of the standards. And that's why you see those 8 science and engineering practices there housed within content, but also being spotlighted as what students do. And our new learning, again, will be what's on the left. And those are the teacher practices. And the final consideration is how might English learners be supported by the student moves and teacher moves? Meaning we want to make sure that science instruction is equitable for all students. And so throughout this learning today, we're going to consider what we can do to provide special scaffolds and opportunities for our English learners.
Hi all, that brings me to introduce myself. My name is Erica Lee. I support science in 3 northern communities. And I am specifically supporting elementary. So as In-Young was sharing, we mentioned the student moves, the science and engineering practices that we have. And in a nutshell, here are our 8 ways that students work to make sense of the natural and human-made phenomenon. So as they are learning the science, we want them to be asking questions or using math and computational thinking, engaging in argument from evidence, which you will see many correlations to English and math practices as well. So for each of the spans, we have elementary, middle school, and high school. These are the practices that are considered high leverage, ones that you will see most frequently on the cast. You'll notice a lot of overlap in SCP2, Science and Engineering Practice 2, developing and using models. Then we see in the secondary grades, analyzing and interpreting data, SCP4. Then across all grade levels, SCP6 and 7, constructing explanations and designing solutions, and engaging in argument from evidence. These are high leverage SCPs. And because they appear most frequently on the cast, we want to make sure that our students aren't just learning the content, right? The DCIs are not just the only things they should be learning, but they should be learning how to do the science. How are they accessing and practicing these skills? So these are the 3 foci that we are going to be focusing on here in LD East. You saw the overlap in those grade levels for SCP2, developing and using models, SCP6, constructing explanations and designing solutions, and SCP7, engaging in argumentation from evidence. So these student moves are really what we want our students to be able to practice and do. That common thread being claim. What is my claim? What is the evidence that I'm going to prove my claim with? And how can I reason and justify these things? And again, you see a lot of overlap here in ELA and in math as well. So we're going to put this into practice. We are going to watch a video and we are going to try to figure out which of these SCPs do we notice most, most strongly. Which SCP are the students engaged in as they are having this conversation? So here's your quick little cheat sheet for you to take a look at. And we'll see it on the next slide as well. So here we have some middle school students engaging in conversation and in discussion. We want you to take a look and see, well, what's the phenomenon? Can we guess what the students are trying to figure out and solve? What are they trying to understand? And which SCP or science and engineering practice are they really engaging in most strongly? And when you're ready, you can share your thoughts in the chat. And after the video is done, we'll also share out.
Question?
No.
Oh, you want to start?
Yeah.
Okay, great.
Sure.
Thank you for raising your hand because you actually don't have to do that. Just sort of speak into the silence.
Oh, okay.
Right, and I'll give you guys a cue if I need you to sort of change gears.
Okay.
Go ahead and start us off, and thanks.
So, there's evidence that it is not incompletely dominant because there's no the glow doesn't vary for the cats. They're all the same amount of brightness. And if it was incompletely dominant, then some cats would be like kind of half glowing and like a low glow, and then others would be more bright. So it is not incompletely dominant because it doesn't vary in brightness.
I disagree with that because I think you're talking about codominance. Incomplete dominance would mean that like it doesn't have to have two alleles of the trait to have the trait, and it also doesn't have to just have one. It varies depending on, well, we don't really know why, but if one parent has the trait and the other parent doesn't, then it depends on whether it depends. Sometimes the cat or the offspring will have the trait, sometimes they won't.
Well, in the article thingy, it said that they didn't vary in glowing.
Yeah.
So that is true, but see up there it says if like you have two copies of the trait, then it will grow more brightly, and if you only have one, then it would glow. It'd have a lower glow, and it said that none of the glows varied.
Yeah,
So.
but for the pedigree, if it was incompletely dominant, then eventually there would be no more ones that are not, well, there'd be much more less ones that are affected, because in the start, I actually think that it's dominant, but for the sake of this purpose, we're doing non-dominant, incomplete dominant and non-dominant. So going off of that, I would say that it's more likely a chance that it be incompletely dominant than non-dominant, because if you're going for the top one and it's I'm just going N, little n, and it's, or big N, because it'd have to be big N to be affected, and then it'd be little n, big N or something. It is possible, but it's much more likely that it's incompletely dominant instead of non-dominant.
Real quick, would it be helpful for the rest of you guys in the circle if Simone drew what she was talking about up here on the pedigree?
Yeah.
Okay, come up and do that. And maybe, Max, you've been trying to talk for a second. Why don't you say what you were going to say while she's working on that?
Well, I was first gonna say what Emma had to say is that where it says 5%, and also I have like drawn up the alleles for the if it was non-dominant, and shown how it's theoretically possible. And it's gonna put it up on the screen after some more. Is that okay?
Okay.
So we can share out in the chat or a small group or type in which science and engineering practice did you notice the students were most engaged in, and what might have been the phenomenon? I see in the chat, Mr. Mesa, we have, or a few people have said 7. What would be your reasoning for why you think the students are engaging in argument from evidence?
The students keep referring back to the actual article, plus there's verbiage or discourse such as "I disagree," and they're going back and forth and presenting their justification for their opinions that they're going off. And I think they're trying to explain why some hats are glowing more than others. What phenomena that might be, I will leave that up to the room to decide.
So I think there's agreement amongst those who have shared out that we're looking at science engineering practice 7. They are engaging in argumentation from evidence, right? And our evidence here from the video is, yeah, the students in that inner circle are bringing up the articles, the reading that they've done. They're sharing some, one student's talking about the alleles that he's drawn up to show, and they're really trying to share with what information they've learned. Exactly. The phenomenon, any guesses what the phenomenon might be? Orchard, I see Miss Melanie, you said, why do the kittens look the way they are? What caused those traits? Okay, we're getting, yeah, that's pretty much on that track. If in the beginning you might have noticed that one of the students mentioned why some kittens are glowing more than others. So there's some trait that's causing some kittens to glow more brightly than others. So they're trying to figure out, well, why is that happening? That is their phenomenon. Thank you for sharing. By the way, there is a little kind of cheat sheet that Miss Inyong Lee had dropped into the chat. So it gives those 3 dimensions of the NGSS in case you need like a 1 or 2 pager, radioactive kittens. I love that. So that is a resource available for you to see. So again, just as a recap, when we talk about NGSS standards-based instruction, we're talking about 3 dimensions. It's no longer just the DCI in the center, what that disciplinary core idea is in terms of the physical science, the life science, or the earth and space science. We're not just talking about content, we're also talking about the science and engineering practices on the left. At least one of these SCPs should be paired up with the DCI that students are learning about, because this is helping them to figure out how things are working. And then of course, we have our cross-cutting concepts on the right side. As we mentioned, it's a lens through which these students are learning and understanding. Are they talking about patterns or cause and effect? And through that all, we want to base it in an anchoring phenomenon. Just like these students in middle school were talking about the glowing kittens. Why are the students trying to figure it out? How does it connect to them?
All right, so I'm Kirsty Hernandez. I am Erica's counterpart for the Northern classes. I am working with secondary schools primarily. So after looking at student practices, now we come in when we're looking at that instructional core placemat. What about teacher practices? What about these teacher moves? So as we go through this next sequence, which Lillian and I will help guide you through, this is the question that we really want in the back of our minds. So we're already thinking about how we can support ELs, but now we want to think, how do we engage students in meaningful forms of science learning? So not just science, because when we think back to science, we think, maybe the way that we learned it, where it's lecture and memorization, but it's not meaningful. We all remember the mitochondria is the powerhouse of the cell, but what does that mean? So in order to do that, we have the ambitious science teaching. There are these 4 practices which we used for our inclusion that we will be exploring in a little bit more depth. So before we go into seeing the ambitious science teaching practices in action, we're going to give you a chance to explore. So we're going to use 5 minutes to review an article and take notes on that article in a note catcher, which I know In Young will be placing in the chat for us. The article is a really short, about 1.5 page document, which kind of gives you an idea of what each practice is. So as you're reading, just jot down a few things, bullet point. What would you expect to see as evidence as you observe classrooms at your schools? Once those 5 minutes are up, we'll put you guys into breakout rooms where you guys can discuss, collaborate, and either add things to your note catcher. Are there any questions? So again, In Young has put both of those links. The first one is the article. The second one is a note catcher, which will have you generate a copy. So we'll start with our 5 minutes for reading and note taking, independent reading and note taking, before we go off into breakout rooms.
Article already?
I'm sorry?
The article, it's in the chat, right?
Yes, the article is in the chat.
Christy, can you retype the article? I just logged back in and out. There was a incident.
Yeah.
Thank you so much.
Oh, In Young just put it there.
Thank you.
All right, so we are going to put you into breakout rooms now and let you guys discuss for 5 minutes. Again, discussing what examples you believe are evidence, adding to your note catchers, and then we'll come back and debrief.
Oh, John, I'll reassign you. Sorry about, Edward, I'll reassign you. Sorry about that. Let's see. Here you go. Oops. All right. Did anyone else want to go to a room?
I think that's everyone has been.
I'm sorry, I didn't hear you.
I think everyone's joined except for us.
Yeah.
Then.
Did you want to go to a room?
Yeah, I can join. I will go to room 1.
I'll go to room 2.
Are you able to choose, or do I have to?
Yeah.
Yeah, because we're co-hosts.
Okay.
Thank you.
Kirsty, and do you guys want to choose first since I don't have any secondary schools?
I'm going to stay here since I'm screen sharing. I'll just not go for today.
I'll stay because I know I need to. We're doing 8th grade. We're doing the speakers. Actually, Soto is doing the speakers right now.
Awesome. Does she have the materials?
She went and she built her own speaker. They just did lesson 2 from that unit. So she said she's going to just try to get through as much as she can before the break. So we'll see how far she gets.
I'll go to room 3 then.
All right. I've done a similar unit to that. So if she needs like someone to talk through things with, I'd be happy to talk through things with her.
Okay. Yeah, I'll let her know because I know that that she's trying that. Lampierre is with 7th grade. I don't know at what point they were. I went to observe yesterday. They were looking at plants. And looking at structure and looking at what the structure of certain things are based on different sources that they had. So, and then what they believe the function of that structure to be. So they went outside and got leaves, and then they had like electron microscope images and other microscope images, and then the different parts where they looked at the underside versus the inside of the leaf. And
have you seen a leaf print done before? Like where you look at a leaf print under, okay, so you can take nail polish and paint the underside of a leaf. And then you can, when it dries, you can peel it off. So you have a leaf print. And then you can put that under a microscope and you can see the stoma. You can see whether the stoma are open or are closed.
Wow, really?
And you can see, and so what's really cool about that is that there's a relative difference in the daytime between opened and closed stoma based upon temperature and their gas release and gas absorption, which is really cool.
Oh, that's really cool.
So you could that could be like a really cool, like you could have prints from the morning and prints from the afternoon, and and then that could be like an investigative question: are they the same? Are they different? Why are they the same? Why are they different?
Yeah, they're funny because they were like the mouth things.
Yeah.
It looks like a mouth. Maybe that's how it like sucks in air or sunlight or hearing their ideas for the function. It was pretty cool.
So I saw a teacher at Wilson do that. This first time I saw it.
Mhm.
And unfortunately, he did it as a confirmation lab. He
Oh.
told them exactly what they were going to see. And then they went outside and they collected leaves and then they did it. They were still so excited about it,
Yeah.
but it was a confirmation lab. And it would have been so powerful if he had just flipped it into an investigation.
Mhm.
All right, they're coming back.
All right, everyone, welcome back. So would anyone like to share evidence that you would see for any of the practices, what you would expect to see when you walk into a classroom and you have a science teacher using these ASTPs? You can unmute or put in the chat.
I can share with what I just observed recently. The first one, it's teacher plans for engagement with important science ideas. So I know it's a work in progress when we go into the classroom about, what's the phenomena. It's like, I have to look up my notes. And so with this one, I went in and I was able to, I see the kids engage. Again, it's grade level, and they were doing the paper airplanes. And some of them, and the teacher was really a facilitator. And I see the kids designing. For some of them are in the process of putting it together already, putting the model. The other ones are still sketching their design. And then towards the middle, after 10 minutes, the teacher said, okay, let's take a look at it. I want a sample. And I want you guys to explain to me. And that's where he embed the questions, the inquiry questions, and also the vocabulary on forces, the motion, and then the velocity. So, and this is a class in which I have my EL and I have my inclusion, my SPED kids. So I was really impressed the way that the kids were engaged. Again, them being able to really participate and really in doing the grade level work for an 8th grade. And it was just really amazing for me to see that everyone are really engaged in the lesson, and they're really so busy. And some are like, Miss, look at what I designed. And it's the impact of it. It's really, I was just really surprised and very impressed with it. So that's one of the, because it was a little bit different for me with the phenomena, but then now I'm like, okay, now I see it, because you get the kids, you're not just getting them, catching them, but rather, and then I went in another week, it continues with the lesson, how he anchored it with that activity, and then it continued with the lessons.
Thank you for sharing. I really appreciate hearing insights into classrooms. It excites me. Edward put in the chat, using anchoring phenomenon, which can be referenced not just in the beginning of units, but any ensuing lessons. So that's an example, some evidence of key practice 1. Multiple learning activities, dissecting lab simulations, showing evidence of their thinking and new learning. Yes, all of these things. Yes, yes, and yes. So what we're going to do now is we're going to take a look into a classroom. And we're going to be looking at an 8th grade class engaging in a phenomena-driven unit about how speakers work. So with each video that we watch, we're going to be looking to see what ambitious science teaching practice is evident. What do we believe that we're seeing? Planning of multiple experiences for students to investigate the phenomenon. Yes, it's not one and done. All right, so we're going to look at our first video segment. And again, as we are watching this video, what ambitious science teaching practice is evident as this video plays for us.
All right, so they need the coil attached to the battery. They need the magnets showing the poles.
Yes.
They need, I think, the speaker adjacent to the coil.
I like that too.
Showing the vibrations. I think that's important.
Yeah, because I think that ultimately shows, like that ultimately answers the question that like this pushing and pulling is causing that speaker to vibrate,
Right,
which is like the bigger thing.
Helps ground them. You know, the kids who are a little bit confused, like, oh wait, that's why we care about it.
Right.
The alligator clips.
Beautiful. How much are we connected to that?
No, there's supposed to be two alligator clips. Two alligators work.
Okay.
No, alligator clips, not oxygen.
Okay.
And
The coil.
Coil line, the coil. All right. I have a question. We've been showing the coil on a lot of these, like head on, like with a circle. But if we want to be showing those forces, it's hard to show the forces coming out of it.
All right, so in the chat, which practice did that video most effectively highlight? 1, 2, you can put 1, 2, 3, 4, you can type it out. What do you think? Or unmute. Two. Four. All right, so the beginning of the video showed us that planning, right? The teacher is planning for their engagement with this idea of how a speaker works. So we're looking at 1, but when you look at the end of the video, you can see he is eliciting student ideas, he is pressing for evidence. So what we're going to learn is that these are all kind of interconnected. So when we go into classrooms, you may not exclusively see just one of these practices at any given point. The second half of the video is put here because when you plan for something, well, the ultimate goal was to have the kids come up with that class consensus models. So they planned these ideas, they planned these series of lessons so that they could essentially create a model to explain how a speaker works. So the practice 1, that planning for engagement, while also incorporating other practices. So now we're going to look at another segment. And again, which ambitious science teaching practice is evident? So as the video is playing, keep that in mind. Which one are we seeing?
Because
read it first. Let me see it, Liz. 5. Five, read up here as well. Okay.
Doesn't make sense. What is the copper's job on the speaker? What does it do?
I think that, what is the what's part? What's the job? The copper. So we're talking about the copper that actually makes up the wire. Does that have a job? I think that's a really important question. It's made out of copper, right? We noticed it was the same material on both speakers, right? Maybe there's something to that. Why do you think it's copper, by the way? Anyone have any? Does it have to be copper? I don't know. Like maybe we should test something like that, right? Okay, put that up there. That's important. All right, you had that in your mind. No one else had a question like that. So when you have something that no one else has, that's not something to be embarrassed about, Markel. That's something that like might push us in the right direction, right? So be proud of that. I want to remind you guys of some of our expectations here. When we're doing this, we got to make sure we're respectful and listening to one another's ideas. We have some amazing ideas. Josh, you want to grab a stool at the table? First time we did this, I remember Markel had a question. I think I brought this up once or twice since. Remember? That you didn't want to share with us at all. Going into that copper about that copper of the coil, right? And it turns out like investing in that copper coil was really important, wasn't it? So sometimes the best questions come from ideas that people maybe don't think are that you want to share them. So I'm going to encourage you, if you've got an idea, especially if it's different, to be sharing it with us. All right? Because sometimes those lead to the most learning. All right, I'm going to.
All right, so again, focusing on that question, which ambitious science teaching practice is evidence, and people are already putting in the chat 3, 2, and 3. But we're also going to focus on what evidence do we have of that. So if you are saying, we know that when we go in and do observations, we need to provide evidence, right? We're calling out this specific practice, but what did we see in the classroom? So what evidence do we have that it is practice 2 or practice 3? Or any other practice for that matter. And you can unmute if it's easier than typing out.
I'm going to agree with Mr. Mesa that it's practice 2 and 3 through the teachers questioning, leading the dialogue around the impact of copper with their unit or lesson of study. It's eliciting, obviously, this particular thinking of student highlighting it. Goes to 3 as well, supporting ongoing changes in thinking. There was a growth mindset context to it that perhaps some ideas that maybe not everyone's thinking about can lead to a better understanding, in this case, of a phenomenon. So 2 and 3 is what I tagged it as. That's the evidence.
Thank you. So when we look at the video, again, we went through that, but we're going to say that this one was most highlighting number 2. And the reason is because they were eliciting those student questions, and those student questions were going to help guide, right? The teacher said, maybe that's something we need to investigate. So that's helping guide the lesson sequence, even if he already had that planned in, his original unit plan. So now we're going to look at our third video segment. And there is a lot going on, but again, that question of just which ambitious science teaching practice is evident. And after this one, we are going to put you guys into breakout rooms to discuss, what did you see, which practice do you believe, and why?
When you flip it, like when it pulls like away, it's like a negative thing.
Okay. So like we're saying, like a pushing force.
Yeah.
Right. Okay. Joshua.
We have a question. When you said what you said, do you mean like if the coil isn't magnetic, what would the magnet have anything to do with it? Is that what you meant? Yeah, then I agree, because if the coil isn't really magnetic, then the magnet can't do anything but just sit there.
I mean, it does do something. It makes it work.
Speak louder so we can all hear.
I mean, it does do something. It makes it like louder, I guess, or it makes it work. It makes it run.
But the coil, yeah, but you can't. You could say it doesn't. You could say it has something to do with it, but you can't really say it's like the main cause, because you basically just agreed that the coil isn't magnetic, and you didn't respond to that. And what I'm thinking is that the magnet isn't the main thing that's making the sound. Like the wires are important, but nobody's saying that that's the main thing. Well, it has something to do with it, but not everybody's focused on the magnet. So, like what I'm saying is that the magnet is necessary, but it's not the most important thing.
Well, I mean, without the magnet, nothing.
Yeah, exactly. But what I'm saying is that it's not the main thing that we should focus. Like, it's not the most important piece, but it's still necessary. Like the wires are necessary, but we're not focused on that the way we are the magnet.
Can you guys speak up a little bit? I think you're having a good discussion. I want us to be able to hear. What's your question, Garden?
So what is the most important?
I don't know. That's what I'm trying to figure out. It could be. I think it is the one. Because it could be the coil. Because without the wire, probably the wires.
Let's hear from Markel. He's had his hand up a little bit.
I feel like that, in my opinion, like everything has like its important role to like the wires brings like the electricity to the iPad or the source or whatever.
Actually, I think I'm more agree with Markel. I think everything, there's not like one most important thing. I think everything's sort of equal because without like the foil, the speaker wouldn't work. And without the magnet, the speaker wouldn't work. So everything relies on each other.
I agree because the wires kind of have to like they attach to the source, and the magnet kind of, without the magnet can't really hear any sounds, and so that's why I need like everything.
Well, I'll tell you what. It sounds like we've got some good ideas. It sounds like we've got some agreement on certain things. It sounds like we're disagreeing on certain things, and we need to investigate more. So I'm going to tell you what we're going to finish up today with, and then what we'll do tomorrow. Tomorrow, I'm going to get all these questions out. I want to figure out where are our questions, what can we do to answer the questions? So like, what can we investigate?
All right, so again, with the question in mind, which ambitious science teaching practice is evident, we're going to put you back into breakout rooms for 5 minutes, discuss which is the most evident and what evidence you have of that from the video clip. So see you back in 5 minutes.
All right, so 11:23, and this is, that was number 3, right? Okay, so we're looking pretty good. We're
I
pretty
think
much
we're at
on.
about the same, yeah, as yesterday.
Mhm.
But no, your story, I mean, your story. It was not too bad, no. It was not too bad. It wasn't too bad. I think it was more intense for you, for you guys. It was the only inquiries I have to deal with was designer 4 to 7. I think that was it. Yeah, I didn't talk to him. I just sent him my stuff.
I'm wondering, I guess.
Yeah. Uh-huh.
Have we trained admin beyond just the big DCI? Because like earlier we were talking about
Like the B and the C and the.
yeah, because one of the admin like said specifically forces of motion PS2, or when they looked at the kittens, they said LS3 heredity, and it's like that is a whole world of what if they're teaching kindergarten heredity? You like I don't even know if heredity is in, but you understand what I'm saying.
Yeah, well, for the DCI, it doesn't specify, like it doesn't specify which grade band. You know,
on the
like
tool, right?
it anywhere. It's like LS1A. It just says LS1A for K235. I mean, it doesn't say, only the PE specifies the grades or the grade band.
Doesn't Appendix 1 specify grade band?
No. So.
Oh, you mean for like the whole? Yeah, so LS1 is just a cross, right? Is that what you're saying? So like 1D, and then it has the grade bands when we get more specific.
Bands, but it's not called LSD, LS2, like it's not called LS2D high school.
Yeah, no. But and I guess that's where my question comes from is, do they understand that there are like grade band specific elements?
Well, they would have had that today had we had our 90 minutes.
Yeah,
And so in general, the APs,
uh-huh.
not so much. It depends on the costs.
Yeah.
So some
So
classes,
my APs not
none
so
of-
much.
in some classes, none of their principals or assistant principals have been trained, or very, very few.
Mhm.
And in others, you know, one group or part of the other has. So
Okay.
it's very disparate between the classes. And so BCM, I mean, they've had, you know, like 6 hours of training on this,
Mhm.
where we've gone into Appendix 1. No, not 6. I guess it was 2 hours. So they've had two 2-hour trainings.
Okay.
HP had 2 2-hour trainings. Those have been the most extensive into Appendix 1, use of Appendix 1. All right, 15 seconds.
Hi everyone, welcome back. I think we're all in the main room now. So would anyone like to share what was the most prominent of the teaching practices observed in the third segment?
I'll go. In our group, we talked about the fact that students were basically kind of sharing their thinking, but we didn't see any evidence of anything with them like backing up their thinking with evidence. So we thought that it was a 3.
That before we move on to our next segment. Okay, we're going to go on to our fourth segment, and in this this is the fourth segment of the unit. We're going to be looking at the fourth practice, pressing for evidence-based explanations. And so as you view and listen to this clip, keep in mind the following question. In what ways does the teacher prompt the students to provide evidence in their explanations? Can you, I'm seeing a message that you can't hear me. Let me put my
I can hear you.
Yeah? Maybe my mic volume needs to be up a little more. Is that helpful?
All right. What are some things that we need to definitely put up as part of this? Yeah.
Horizons, you should somehow show like electricity going like through the battery, through the wire.
All right. Do you guys all agree we should show electricity and a battery in the wire?
Mm-hmm.
Yeah?
Wait, we're doing step by step, but like just putting it.
Well, I want to be able to put a model up here.
Yeah, I know. But
Right. Do you agree with what Markel said? All right. Did everyone agree that we should put a battery up there?
No. iPad.
An iPad?
The iPad,
Right. So
no, but it doesn't switch the current.
Say that again?
The battery doesn't switch the current.
The battery doesn't switch the current, so you're saying the iPad switches the current. Is that important to figuring out how the speaker works?
Yes.
Okay, so what should we show it connected to?
battery.
I'm still hearing battery and iPad. Why should it be the battery and why should it be the iPad?
iPad can switch the current.
And what? What's that?
It switches screens.
Right? Remember from the reading?
Oh, I thought, no, because Anthony said that something about.
What? Said that.
Oh, never mind. That makes so much sense now. Yeah.
All right. And why is that important that the iPad switches the currents? Why does that matter?
Vibrations.
The magnet.
Hold on. You are skipping step 1 and step 2, and you're going straight to step 3. I agree that switching the current gets to vibrations, but how? What are the steps in between?
So, forcing the change.
So it switches between repulsive and attractive forces, which cause the vibrations, which causes, perfect. All right, so I'm gonna draw an iPad in here. I'm just gonna put it over here. Does that sound okay? I know what you guys are thinking. That looks exactly like an iPad. No. You're welcome. I'm really hard. What should be connected to the iPad? What do we say?
The wire. No.
The aux cord. The aux cord. Beautiful. And what is connected to that?
Okay, so would anyone like to share, type in the chat or unmute themselves? What did we see? In what ways did the teacher prompt students? Sorry for the background noise, there's construction going on.
I can speak. Can you hear me? So at the one point when the student was trying to explain something and jumped all the way to the last step, the teacher stopped and said, okay, but you're skipping steps 1 and 2 and you went all the way to 3. So can you go back? So forcing the student to slow down, go back, use the specific evidence before just jumping to the last step of it.
Yeah, and I think also they were using a lot of whys and hows, questions, why so-and-so does this and how this so-and-so does that. So the students were, again, trying to kind of put them in sequence, from what happens first, what happens second, what happens third, So finding the connection between the iPad to the speaker or to the speaker to the iPad. And so a lot of also visual learning, drawing something on the board was prompting them to participate in the discussion.
That's great observations. Thank you, Jessica. And I think that was Esther. Did anyone else want to add anything?
I just was going to say that he kept repeating, like what the students were saying. So he validated what they were saying and connected just so that it resonates with them. Okay, so what's next? So you said this and what's next? So it validated their thinking to see what was coming next.
Fantastic. Yes, thank you. Hi, Sandra. Yes, exactly. And so you noticed, yeah, he was creating a model to help the students really understand that, create that causal explanation, and to help them build that gapless explanation towards the end of the unit on how the speaker works. So that was the example or evidence of some sample of the practice 4. So we're going to take a look at the 5th and final segment of this series and think about in what ways was student voice amplified. So thinking back at those instructional levers and where our focus is also student voice, as we watch and view this, listen to this video, think about that student voice and how is it amplified.
You can really be scared to put the power in the student's hands. That's not traditionally, especially at a middle school, where kids are just crazy. We know middle school kids are crazy. And so asking them to, basically develop everything that we're gonna learn in the unit is unthinkable at some level, right? The magnetic field that the kids are starting to draw and understand, I didn't see that till I was in college. And to think that, middle school kids are going to be able to do that, that when I first saw that, I'm like, yeah, right, that'd be nice if they could come up with that and think about that. But they really did. They really did develop everything through this unit, and that's powerful. And that, I think, the hope is that it's not just the open SciEd units themselves that are going to be taught this way, but that these lessons, these practices can be applied towards every lesson, towards every unit. Maybe teach something a little bit different next time you go and teach, unit XYZ, where it is relying more on the students, where it's not verified by the right answer at the end of the class. And I think you know, the ways that I've seen certain students just change and their eyes light up in a way that they don't during a more traditional science unit. It's so powerful. And you know, like this is how kids develop a love of science.
Like during the speaker unit, we were like going over how the speaker worked, and yeah, we were going over how the speaker worked itself, and we weren't really like guided by the teacher. We made like our own path, so it was more difficult, but it's not like we were just reading off a piece of paper, and I think we learned more from it.
I feel like it's better because like it's in a higher level of science, where we're the scientists. We have to figure out stuff. What my class did in this unit that I would like to see in other like just classes in general is working together. We work together a little bit, and basically how like the students did lead the class a lot. I would like to see the kids and students leading the class a lot more than they usually do.
And why do you like that, like leading the class?
I like leading the
Why
class.
is that good for all subjects?
It's good because it gives the students like the basic skill of leadership and independence.
Okay, would anyone like to share how student voice was amplified in this unit and in this series?
I'll share. Go ahead.
Go ahead.
Okay, so students just felt like more empowered. They said that they were the scientist. They were able to lead the class. They got to work together. It taught them leadership. And it doesn't sound like it's something that they're used to doing, but it's something that they want to continue doing. And I liked when he said it was more difficult, but we learned a lot more. And I thought that was like key right there, because he recognized that it was challenging, but it was worth it. So I thought that was key.
And for me, what I saw here is from the teacher. I saw the teacher more directing the students as opposed to correcting the students. So making sure that engagement continues, that engagement is enhanced, that engagement is powered up. So the teacher is, rather than correcting them, he's directing them so that to go to higher level of thinking. For the students, I think I saw more communication on them instead of separation. So when the kid says, this is a good idea because you get to, we're together, so they're communicating in one subject area, which they all know and they have something to say. Whereas if we put them in independent studies and put them independently, they feel pretty much separated. So I think in that one, communication was more impactful than separation as far as the students are concerned.
Fantastic. Well said, Felisa and Esther. Thank you so much for sharing. And yeah, this is just my favorite clip. And I said it yesterday, like at that last segment, I just want to hug that student, be like, yes, exactly. This is great. But okay, so we're getting close to the end, so we can go on to our next slide. Just a quick resource from our instructional core placemat. There's a couple of other examples there, along with links to primers that describe each of the key practices a little more in depth. So that resource is available for you when you start, when you continue with your classroom observations in science. And Inyang has placed a link to the instructional core placemat in the chat if you'd like to grab that. So one final part for me is the part about how might these practices support English learners. Think about, you can go back to that slide 31 with those evidences and see how the different practices help support each of our diverse learners and English learners as well. Okay, and up next is Tara.
Thank you so much. So
connecting to what you were just sharing about how do we support our English learners, one way that we can help to elevate our students' voice in the classroom is using the conversation flip charts link that you will see in the chat box. This flip chart contains both response and prompt starters for our students, and this is going to help all students, but most especially our English learners. These are aligned to designated ELD and the conversation starters that were developed by Jeff Sweers that are, research shown to really support student voice and language across content areas and definitely in science. So we hope that you find this resource helpful. Thank you.
Thank you, Tara. So how does today's learning support our LD East instructional levers and drivers and board goals? We're hoping that you're making the connections to that as we've gone through today. We're going to invite you now, as we're closing out our piece here, to click on the link that's going to appear into the chat for a reflection on this learning piece that we've had with you today. We want to thank you for your engaged participation. We've had some wonderful opportunities to hear your thinking and that you were sharing your thinking with each other. It was a great moment of reflection for me as I was listening to you. Please share your reflections and thoughts at the link. And then we're also going to, after you're done with that, we're going to invite you to return back to the main room. But on behalf of the presenters today, Erica, Kirsty, In-Young, Lily, and Tara, and myself, I'd like to say thank you very much. Our contact information is here. In-Young has shared with you the link to the presentation slide deck. And once you're done with the reflection, then please rejoin the main session for the closing message. And the link is now in the chat. Thank you all for coming today. We appreciate you and all of the hard work that you do for our kids.
Thank you.
Hey, Craig. Thanks for the link.
Hey, Juanita, how are you?
I'm good. I'm sorry I was late, but we'll talk.
Hi, Miss White Holloman.
Hey, Miss Young. How are you? Am I going to see you Monday?
I sure am. I'll be there.
Awesome. Awesome. All right, guys. I was late and I had to go back to live with a parent, but have a great weekend.
You too.
All right. Bye-bye. Let me show this link.
It's beginning to look a lot like Christmas everywhere you go. Take a look at the 5 and 10. It's glistening once again with candy canes and silver lanes that glow. It's beginning to look a lot like Christmas.
Hey, Enya, who sings this?
Toys in every store.
Michael Bublé.
But the prettiest
My
favorite.
Yes, Michael Bublé makes you feel like it's Christmas.
I only
All
like
year
him
round.
for Christmas songs.
What?
Only for Christmas, not for other stuff.